We're going to talk about cubic function. Okay, start getting into that a little bit. Also going to talk about something called a power functions. Going to look at a few different characteristics of that. And a big part of today is also getting to understand how to find what is called the end behavior, which we'll talk about that whenever we get there. Okay. So first, talking specifically about cubic functions. A cubic function can be the product. What operation is product talking about? Multiplication. So it is the product of three linear functions or one linear and one quadratic. All right, that's going to be a lot of this unit. That's kind of what we're going to do down here is finding the product. Looking at number 3. I'm multiplying x times x squared minus 5x plus 7. So there is your linear, and there is one quadratic. All right, make sure that you can identify what it is you're multiplying. This one is pretty simple. All you have to do is distribute that x. You end up with x cubed minus 5x squared plus 7x. Okay. Going to number 4. Whenever we've done FOIL is an acronym that is specific to two binomials. Okay. But whenever you're doing a binomial and a trinomial, it's the same idea, just to the next degree, I guess you might say, or to the next level. So all I'll do is I'm going to take that h and I'm going to multiply it to all three terms over there. So I've got h cubed plus 6h squared minus 11h. After that, I'll take 4 and I will distribute it to those three terms right there. So I have plus 4h squared plus 24h minus 44. Once I'm done with that, I'll go through and I'll combine my like terms. So I've only got one h cubed. Then I've got 6h squared and 4h squared. Those will add to 10h squared. I have negative 11h plus 24h, which is plus 13h. And then I have minus 44 at the end. Going to number 5. So this is 3 linears. Okay, I know they're all linear because they don't have squared on them. So whenever you're multiplying 3 linears, you're most likely going to have to do FOIL for the first two. So that is going to give me 6x squared minus 4x plus 3x minus 2. I can combine those two middle terms to get 6x squared minus x minus 2. And then you're going to multiply that by 4x minus 3. Now I had someone in first period ask me is it okay if I write that 4x minus 3 up front. Is that doing the same thing?
No. Yes.
Yes, I'm multiplying, right? So to give a simplified example of that, is 3 times 4 the same thing as 4 times 3? Yes. Okay. So I want you to finish that problem from there. And then on number 6, you've got x minus 3 cubed, so that means you have 3 x minus 3's. I want you to take that one from that step. You've got to be very careful on these problems. There are a lot of little spots to make errors on. Okay. The good thing about that is, as long as it is just a small error, come test or quiz time, then it's only going to be partial credit. So you'd have x squared minus 6x plus 9, and x minus 3. Whenever you multiply those, you'd have x cubed minus 6x squared plus 9x plus 3x squared plus 18x minus 27. And that comes out to okay, so make that one small adjustment. Negative 3x squared, which changes to negative 9x squared. Whenever we had a quadratic and we factored it, we had two roots. Okay? You need to know whenever we have cubic, you may end up with something like this, to where you may end up with 3 roots. Okay? Whenever we have x to the 4th, you may have 4 roots. And it's going to keep building from there. Alright? Now, we're not going to go get too crazy with the polynomials we're going to build in here. But we will need to know the basics kind of going forward. Okay? So, on looking at just the parent cubic function, so all the cubic functions will be based off of this right here. Alright, increasing. If it is increasing, how, and I'm going to kind of correlate this with the end behavior. It is coming from the bottom, and it ends up going up. Okay, so I want you to write down up right there, because it's coming from down here, and it ends up going up. So it's an increasing graph. Alright, so next we're going to talk about this end behavior. And whenever you do end behavior, what I've had some kids in the past do, actually I think it was last year, I noticed a student was doing this and they said that it really helped them. And it's something that a lot of you probably, you already know that's the way it is. That up goes to infinity and to the right goes to infinity, but that just helped them. So every time you write the end behavior, this is how you're going to write it. As x approaches negative infinity, y approaches, is how that is pronounced. As x approaches positive infinity, y approaches. So go ahead and write that down, and then we're going to talk about that and kind of what we end up putting in there at the end.
What is y approach?
Follow my highlighter up here on the graph. If I start really anywhere on the graph and I move towards infinity, so I move to the right, does the y value, is it approaching infinity or negative infinity? Infinity. So that's actually the second one. I should have done the first one. So that's as x approached infinity. The first one, the negative infinity, that means that I'm going to the left. Okay, I'm going towards this negative infinity. The y value is approaching what? Negative infinity.
Is there always going to be matching?
No, not always. We'll talk about those on the back. You see that? If you're a pre-cal bound, you need to make sure to understand that concept. All right. With as many times this year as you've seen domain and range, next year a lot of times in multiple units you'll see domain, range, and behavior. Okay. So the good thing about the domain and range on this one is, barring some word problem that restricts the domain and range, that is always your domain and range for every cubic function. the x-intercept and the y-intercept, it's both going through the origin. Your critical points are -1, -1, 0, 0, and 1, 1. What I mean by critical points is whenever you get to the, you don't have to put this in here, whenever we get to the transformation lesson, those are those points on the outside, and then you know your transformations in here. The right 1, right 2, right 3, the other way that I taught that, you can still do that for cubic. There's a little tweak to it though. Okay, it's not hard, but it's obviously it's not quadratic, so it's not the same. This is symmetric about a point. Okay, so what that, or in this specific point, is the origin. All right, so what that means is that if I go right 2, up 8, the point on the graph that is reflected around that point of symmetry would be -2, -8. All right, whereas if it was a parabola, we would go -2, up 8, and you would get that shape. Okay, but this one goes down so that you end up with
So it's like half a parabola.
what the graph looks like.
And the other part's just like
It's like half of the parabola is reflected across the x-axis. Okay, and then this side is, yep. Okay, so let's go down here. There's a lot of blank space down here. We're going to kind of fill it in with some different characteristics, some things you need to be aware of as we go through this unit. So the first thing says a power function is a function, it says p of x, could be anything, is a times x to the power of n, where n is a positive integer. So, and we're going to talk about these in a couple lessons, the power function versus what we'll call the polynomial function. Okay, but your power function is y equals a times x to the power of n. There's not a second term. It's just one term, and it's the majority of the time it's just going to be x to a certain power. Okay, just to give you an example of it, you might have y equals x to the power of 7. All right. That compared to what we're going to call a polynomial function. That is going to be y equals ax to the power of n plus bx to the power of n minus 1 plus cx to the power of n minus 2, and so on. Whenever you see the example of this, it'll probably make a little more sense than what that looks like. So an example of that, I'll just stick with, we got 7 over there. So if I had y equals 2x to the 7th, the next term would have, the exponent would be minus 1, so it would be to the 6th. And then the next exponent would be 1 less than that. And then the next exponent would be 1 less than that. Okay, and that can go all the way down until it's just the x term and then just the number at the very end. Okay, so polynomial, power function. Make sure that you are good on the end behavior. Again, a lot of emphasis on that today. That make sure you know how that always starts. As x approaches negative infinity, y approaches. As x approaches positive infinity, y approaches. And then you'll always fill in that right there. And we've already kind of talked about that in behavior already. Whenever I refer to the degree of a polynomial, all I'm talking about is the largest exponent. So if you look at this one right here, this would be considered a 7th degree polynomial because the largest exponent is 7. If I didn't have that first term, and it started off with 3x to the 6th, that's a 6th degree polynomial. Okay?
The biggest, that's the biggest.
It's the large. It should be if it's written correctly, it's the first exponent. Okay. Now, depending on whether that degree is odd or even, we're going to kind of talk about the symmetry here between those two. An odd degree, so the x cubed we just talked about, those are going to be symmetric about a point. Okay, kind of what we just talked about, it was symmetric around the origin. If it is even, it is going to be symmetric about, oh, that didn't do what I wanted it to do. Symmetric about a line or axis. Okay. Okay, so these are just some things that you need to be aware of going forward. Okay, the difference between a power function and a polynomial function. Make sure you're good on writing your end behavior. Whenever I say, all right, we're dealing with a 5th degree polynomial, you know what that means. Okay, so
The exponent is 5.
so the largest exponent is 5. All right, so let's go to the back. So going to the back, you've got a lot of examples of power functions. All right, y equals x, the linear one. Oddly enough, even though that's the simple one, that's the one that looks the most out of place up there. Okay, all the other ones, all of my even degree ones, okay, 2, 4, and 6, they all look kind of the same. 3 and 5, they look kind of the same. All right, and what makes them different, or I guess what makes them similar, is that, okay, 2, 4, and 6, those are all even exponents. And they all look like a parabola. It's just that down here close to the vertex, it looks like it just gets wider and wider, or it kind of gets flatter down there, however you want to see that. All the other ones are odd degrees. Okay, and notice how they all end up. You know, earlier whenever we had the cubic, I called this one a down up because it started down here and it ended up here. Well, all my even degrees, it starts up here and it ends up here. So we would call those up, up. Here in a minute, we'll do that whenever we're looking at the end behavior stuff. Okay? You've got all these. All of your even degree are symmetric around that line. Okay, if it's just a power function, it'll be the y-axis. All of your odd degree are symmetric about that point. Okay, and so that's how you would find those reflected points about the line. Instead of going left and up, you'd go left and down. Okay, so there's examples of the different power functions that you'll see. Now down here at the bottom, we're going to fill this in. Zoom out a bit. Okay, we're going to fill this table in. And even though, and just this is for end behavior, which it doesn't say on there, which would be probably good to write it above the table. We're going to write the end behavior for all these different situations. Now, these say power functions. This is going to be true for all even and odd degree polynomial functions, which we're going to compare it all in a couple lessons from here. Let's get this up some. Okay. So if that A value is greater than 0, which is another way of saying positive. Okay, off here to the right, to the left of the table, I want you to write this. A little arrow going down, kind of from a cloud looking shape, and an arrow going up. And I'll talk about what that means exactly here in a minute. But think about the cubic function that we looked at earlier. All of these odd degree polynomials that are positive, they're going to be considered down up. And I'm going to write my end behavior, write that beginning part of the end behavior. Whoa. Okay. So if you count this, reading the graph from left to right, and it's a down up, it starts down here, it ends up going up. That's going to tell you whether to do negative or positive infinity. Okay. Down would obviously tell you what? Negative infinity. Up would tell you what? Positive infinity. Okay. If the A value is less than 0, that's going to make it negative. So that means the whole thing is reflected. So the little cloud thing that I want you to draw is that right there. Starts up here, it ends up going down. So this one we would call up, down. So as x goes to the left, if this is going up, y is approaching what? Positive or negative infinity? Positive. As x goes to the right, y is approaching what? Negative infinity. So get that one written down. Okay, so what the cloud thing means. It is not going to be uncommon for us to have a graph that might look similar to this. Okay, in fact, that one's pretty basic. We could even have one that does this. Okay? So what the cloud means is all those curves in the middle that you're all looking at wondering where did I even get that? Okay? Because it doesn't matter what's in there. Whenever I'm talking about the end behavior, all I care about is where did it come from and where is it ending up going. That's all I care about. There's going to be all kinds of garbage in here once we get to those polynomial functions. Okay, up, down, we'll talk about something that's called a twist. It's not near as difficult as it sounds, I promise you that. But it looks difficult now. Yeah, don't give me that moan. Okay, so let's go to the even degree. So kind of think about a parabola. It starts off from up there, goes down, usually hits the does hit the vertex, ends up going back up. So this would be an up, up. So if they both go up, both of my y's are approaching what? Positive infinity. And then if it's negative, everything reflects. All my ups turn to downs because it looks like that. That would be a down, down. And both my y's would end up approaching negative infinity. Now look up here for just a second while I show you something on here. Even though I compared that to parabolas, alright, stop writing and look up here real quick. Okay, that cloud, once we get into higher degree polynomials to the 4th, to the 6th, to the 8th, it's still going to end up doing that. But the same thing as I drew over there, okay, it may do something like that. But that's what that cloud means. All that garbage in there, I don't care. I care about where it came from and where it's going. That's all I care about when I'm thinking about in behavior. Okay? So make sure that you have all of this written down. There is a lot of emphasis on this. The last question, not the last question, but before the last 4 questions on your homework that talk about in behavior, you're asked to fill this chart out again. Okay? So you can understand that, we need you to know this, especially going forward into pre-cal, because they do talk about this quite a bit.